Have you ever wondered why your phone heats up when you use it for a long time? Or why an electric bulb gets hot? Well, the answer lies in something called Joule heating. Now you might ask, what is Joule heating? It's also known as resistive heating, a phenomenon where electrical energy morphs into heat energy. Imagine this. Electricity flows through a conductor, much like water flowing through a river. As it does so, it collides with the atoms or molecules in the conductor, much like water rushing against the riverbed. These collisions transform electrical energy into thermal energy, causing the conductor to heat up. This process, my friends, is what we call Joule heating. It's named after James Prescott Joule, a physicist who explored the intriguing relationship between electricity and heat in the mid-19th century. So get ready as we dive into the fascinating world of Joule heating. Before we delve deeper, let's understand some basics. What exactly is a conductor, and what is an electric current? A conductor, in the realm of electricity, is something that allows electric current to pass through it. Picture it as a highway for electrons. It's the pathway that these tiny charged particles use to move from one place to another. Common conductors include metals like copper and aluminum, largely due to their ability to allow electrons to move freely. Now, let's talk about electric current. An electric current is simply the flow of electric charge. You can think of it as a river, not of water, but of electrons. When you switch on a light or start your microwave, you are basically allowing this river of electrons to flow, and this flow is what we call an electric current. But how does this flow happen? Well, it all starts when a potential difference or voltage is applied. You can imagine it like a slope along a river. The steeper the slope, the faster the water will flow. In the case of electric current, voltage acts as the slope, pushing the electrons along our conductor highway. However, this journey of electrons isn't always smooth. As they move along the conductor, they often collide with the atoms of the conductor material. Imagine it like a bustling city during rush hour, with cars, our electrons, bumping into each other and causing traffic. These collisions are what lead to the conversion of electrical energy into heat, a phenomenon we know as Joule heating. Now that we have a basic understanding of conductors and electric current, let's see how these two interact to produce heat. This interaction is crucial in many aspects of our daily lives, from keeping our homes warm to lighting up our nights. But as we'll see, it also has its challenges and requires careful management to prevent energy loss and potential damage. So buckle up as we journey further into the fascinating world of Joule heating. Imagine a busy road filled with cars. These cars are like the electrons in an electric current. Now think of these cars moving along the road, each with a destination to reach. As they speed along, they encounter obstacles. Other cars, pedestrians, traffic lights. Each time they collide or slow down, energy is lost as heat due to friction between the tires and the road surface. In a similar way, when an electric current flows through a conductor, it's like a highway of electrons. These tiny particles, each carrying a negative charge, zip through the conductor with a certain amount of energy. But the conductor isn't an open freeway. It's more like a bustling city street. The electrons encounter atoms or molecules within the conductor. These atoms and molecules act like obstacles on the road, causing the electrons to collide with them. Each collision is like a little traffic accident. The electron doesn't come to a halt, but it does lose some energy in the process. And just like the heat generated by a car's tires on the road, this energy doesn't disappear. It's converted into another form: thermal energy or heat. This is why when you touch a wire carrying a current, it may feel warm or even hot. Now, the more cars or electrons there are and the faster they move, the more collisions occur. Similarly, the higher the electric current, the more heat is generated. This is why a wire carrying a high current can become very hot. On the other hand, the resistance of the conductor plays a significant role too. Going back to our car analogy, imagine the difference between driving on a clear straight highway and navigating a narrow winding road filled with obstacles. The latter would cause more friction and generate more heat. In the same way, a conductor with higher resistance, meaning it's more difficult for the electrons to move through, will produce more heat when a current is applied. But it's not just about the number of electrons, their speed, or the resistance they encounter. The length of time the current flows also matters. Think about it. The longer you drive your car, the hotter the engine gets. Similarly, the longer the current flows, the more heat is generated. So just like a car engine heats up due to friction, a conductor heats up due to the collisions of electrons. This, in a nutshell, is Joule heating. Now you may wonder how much heat gets produced. Well, there's a law for that. It's called Joule's law, named after the physicist James Prescott Joule, who explored the relationship between electricity and heat in the mid-19th century. Joule's law allows us to calculate the amount of heat produced when an electric current flows through a conductor. Here's how it goes. The heat produced, denoted as Q, equals the square of the current, denoted as I, times the resistance, denoted as R, times the time, denoted as T. In simpler terms, if we have a wire with a certain resistance and we let an electric current flow through it for a certain time, we can calculate the heat produced. The equation is Q equals I squared times R times T. Let's break down these components one by one. First, we have the heat produced, Q. This is the thermal energy released as the electric current passes through the conductor. Next, we have the electric current, I. This is the flow of electric charge through the conductor. The more current, the more collisions between electrons and atoms, and hence more heat is produced. Then we have the resistance, R. Resistance is a measure of how much a material opposes the flow of electric current. A higher resistance means more energy is needed for the current to pass through, which in turn produces more heat. Lastly, we have time, T. Simply put, the longer the current flows, the more heat is produced. Let's imagine a simple example. Suppose we have a small electric heater. If we increase the current, the resistance, or run the heater for a longer time, the heater will produce more heat, making the room warmer. So, the amount of heat produced depends on the current, resistance, and time. More of any of these and you have more heat. This is the essence of Joule's law, a fundamental principle that governs the relationship between electricity and heat. Joule heating isn't just a science concept, it's everywhere around us. This principle comes to life in many everyday objects that we tend to take for granted. Take, for instance, your electric heater. It is a perfect example of Joule heating in action. When an electric current passes through the heater's wire coil, the resistance causes the wire to heat up, thereby warming your room. Similarly, the humble incandescent light bulb is another prime example. When electricity passes through the filament, the resistance causes it to heat up and glow. The glow you see is essentially Joule heating turned into light. Even the electric stove in your kitchen uses Joule heating. The electric current heats the stove's elements, enabling you to cook your favorite meals. But it's not just about warming rooms, lighting bulbs, or cooking food. Joule heating also has significant implications in areas where it needs to be minimized. Think of your smartphone or your laptop. Ever noticed how it gets warm after a long use? That's Joule heating at work. Here the challenge lies in managing this heat. Excessive heat can lead to energy loss, reduced efficiency, and even potential damage to the device's components. This is why the design of these devices often includes measures to control Joule heating. The conductors used in these devices are made from materials with low resistance. Some devices even have built-in cooling mechanisms to dissipate the heat. Joule heating, named after James Prescott Joule, who studied the relationship between electricity and heat in the mid-19th century, is an integral part of our lives. It is a principle that has been harnessed for our comfort and convenience. But it is also a challenge that requires careful management in our increasingly digital world. So, next time you feel your phone getting warm, or you see a filament glowing in a bulb, you'll know that's Joule heating in action.